Hello, and welcome everyone. My name is Florin Stingaciu, and I'm a product manager here at Google. I'm really excited to be here today. Thank you for joining us for this breakout session on defining security guardrails with access and organization policies. So, what are security guardrails anyway? Well, detection and remediation of security vulnerabilities or threats is expensive and often too late to prevent severe impact to your business. At Google Cloud, we take prevention seriously. To help customers make the shift towards a preventative security posture, we have been investing in security controls that allow administrators to establish effective security guardrails that protect your resources and data. Today, you will hear from Box and Snap on how they establish and mature their security guardrail framework. And while they share similar security goals, Box and Snap started their Google Cloud journey from different points. Snap was one of the first few GCP customers, and their security guardrail approach has continuously evolved over time. While Box has had the more recent migration to GCP, which has given them a chance to design their security guardrail from scratch. Despite their different history, GCP's security guardrails were flexible enough to allow both organizations to establish a mature security guardrail framework and meet their security goals. You'll hear more about this shortly, but first, let's do a round of introductions. Alongside me today, we will have Matt Bose, Senior Staff Security Architect at Box. We will also have Babak Bahaman, a Production Security Manager at Snap, and Akshay Datar, a Product Manager from Google Cloud. And with that out of the way, Akshay and I will first cover a brief overview of GCP security controls that can be used to establish effective guardrails. Starting off with why adopt this type of approach in the first place? As an enterprise continues to scale their cloud footprint, it becomes very difficult for a centralized security administrator team to rely on reactive controls to enforce their security posture without impacting developer velocity. In addition, violation detection and remediation adds toil and cost. Instead, these security teams rely on establishing a security guardrail framework, shifting their security posture towards a preventative approach. This allows administrators to establish a developer self-service model for access management capabilities that is in compliance with their organization's security requirements. This model reduces the burden of having to process access management requests, resource configuration violations, or other similar security issues. Let's take a look at some of these controls. And as I'm sure you already know, IAM allow policies are fundamental security controls that allows administrators to manage access controls for resources they own. However, IAM allow policies on their own do not establish guardrails to enable developer self-service, nor do they shift the security posture towards a preventative approach. Instead, IAM deny and organization policies are the fundamental primitives for establishing security guardrails on your resources and data. Now, in order to adopt these controls safely and at scale, Google Cloud also provides intelligent policy lifecycle management tooling that simplify administrator operations, enable policy-safe rollout, and power compliance reporting. These tools, combined with these primitives and Google's machine learning capabilities, deliver a complete framework to allow administrators to establish an effective security guardrail approach. Let's cover each of these primitives as well as some of the policy lifecycle management tooling in more depth. And really, the first layer in our Defense in Depth tool suite is IAM Deny, which allows administrators to explicitly deny access, overriding any existing or future IAM Allow policies. IAM Deny is a resource-centric control, which means the policy is attached to the resource. And once attached, this policy captures a list of permissions that will always be denied when performed by a set of given principals. These principals will never be able to perform those actions on that resource, even if an IAM Allow policy grant explicitly allows access. This can be used to enable developer self-service and minimize the amount of access management activities by the centralized security administrator team. This team can grant developers wide access to their environment and use IAM Deny to prune or set guardrails on the overall permissions that can be executed within this environment. For example, imagine an organization that is highly focused on delivering machine learning models to their customers. They probably have a quite large data science and data engineering department. Now, these teams rely on autonomy, especially the developers. And a centralized security team could not possibly keep up with all the access change management requests or other security control changes without impacting their velocity as an organization. Instead, the centralized security team could grant wide access to the development environment and define a number of key IAM deny policies that prevent unauthorized actions. For example, you could have a deny policy that prevents this team from purchasing BigQuery commitments or from creating service account keys. In this example, the team was able to control costs as well as prevent unauthorized service account key leaks while at the same time enabling developer velocity within their environment and giving them as much flexibility as possible in the way they operate. Now, since IAM deny policies can be applied at any level of the resource hierarchy, this is a very powerful security control that you have in your toolbox. And in addition to preventing actions on resources, you will now hear from Akshay, who will talk about how to enforce restrictions on resource configurations.
Datar, I'm a product manager here at Google. A key resource-centric layer is organization policy, or org policy, which allows you to control which resource configurations are permitted in your organization. Org policy is a fundamental native GCP control that allows you to control or protect your resources independent of principles or resource actions. And just like IAM deny, administrators can apply this guardrail at any layer or any level of the resource hierarchy. Org policy service inspects each and every, at configuration time, it inspects each and every resource action, and non-compliant requests, such as creating a non-compliant resource configuration or updating a resource to a non-compliant state, will get rejected. Some really popular use cases for org policies include restricting locations where resources are permitted for local compliance reasons, restricting external traffic to protect against breaches and exploits, and ensuring that you only use hardened and trusted images for your resources, and many, many more. There are essentially two types of org policies that GCP offers. First, we have a set of predefined, pre-built org policies that we have identified based on industry best practices, feedback from customers such as yourselves, as well as red team findings. These are hard-coded and they are ready to use for you. Second, I am really pleased to share the public preview availability of custom org policies for GKE, GCE, and Dataproc. With custom org policies, you can author really fine-grained, tailored guardrails specific to your unique security requirements using easy-to-use, easy-to-read, common expression language-based logical conditions. As an example, consider a use case where you have, you want to ensure that only trusted images are used for your GKE applications or GKE workloads, and only in certain sensitive environments. You can easily set up this org policy, this custom org policy using the framework that I just described, and effectively you reduce the amount of time needed to make policy changes down to minutes and hours. Now, in order to safely adopt and scale these guardrails in your organization, like Florin mentioned, GCP offers a suite of policy lifecycle management tooling. We cover the entire lifecycle of your resources, from designing effective configurations to deploying resources and detection as well. So recommendation tools like IAM Recommender leverage Google's ML expertise to help you design an effective security posture. Once this posture is designed, in order to deploy it safely and securely, we have a set of tools that allow you to do that as well as part of our safe deployment tooling. For one example is Policy Simulator, which allows admins to understand the impact of policy and posture changes on existing resources. Similarly, you can also set policy and posture changes in dry run mode to understand how they would behave in the real world through audit logs. And finally, GCP offers a robust set of detection and troubleshooting tools which help you monitor, for example, the state of compliance using policy analysis, triage errors through troubleshooting, and identify drift through violation reporting. Now that we have covered a few basics about how we approach security guardrails, I would love to invite Matt over to showcase how Box uses our controls for security guardrails in Google Cloud.
Thanks, Akshay. Hi, I'm Matt Bose. I'm Senior Staff Security Architect at Box. I came to Box about 3 years ago during the start of our GCP migration. My mission was to build a secure foundation for GCP that would allow us to migrate our on-prem data center to the cloud. Today, I'm going to tell you about Box, our security culture, how we implement prescriptive security guardrails, and lastly, what security features we're excited about in GCP. A little about Box. Box is a cloud content management platform with almost an exabyte of data being stored, shared, and collaborated on. We have a customer base of Fortune 500 companies, government entities, and individual users. At Box, we're a you build it, you own it culture. We perform all production changes via code, and we have centralized teams that control foundational services such as networking, project creation, IAM, and so on. The security goals that I'm going to discuss are to implement prescriptive security guardrails, to follow the principle of least privilege, and to improve developer velocity by providing feedback early in the development process. To accomplish our goals, we take a defense-in-depth approach and apply multiple security guardrails to our organization. Today, I'll discuss 3 of these guardrails. First, we have org policies. Then we'll talk about our least permissions model that we govern via IAM policies. And finally, we'll talk about our infrastructure as code policies. Org policies are part of our secure foundation. They allow us to establish preventative guardrails to restrict what actions can be taken. They simplify operations because they can be set once at the root of the organization and propagate out to all resources. We prioritize evaluating and implementing org policies at the beginning of our GCP journey to ensure that our infrastructure was built securely from the start. Our first priority with org policies was to restrict public access and to only allow Box identities to be added to Box IAM policies. We didn't apply every policy. We selected the policies that would help us meet our requirements. We manage all of our org policies via code. We store them in a central location, and one team is responsible for org policy changes. We apply most policies at the org level, and they're inherited to all the entire environment. And to provide a consistent experience, we try to keep the policies the same in each environment. There are cases when environments or projects will have different policies. One example is we have an external IP constraint that blocks public IPs. But we have specific networking projects that need the ability to use these public IPs. For those projects, we'll set an exclusion and we'll allow them to provision public IPs. This allows us to reduce the risk of exposing our workloads to the internet, except for the exact workloads that need it. Next, I'll talk about our IAM policies. Our least permissions model, which is governed by IAM policies, is a core concept in our security strategy. When we decided to move to GCP, we had to figure out how to implement a least permission process. We had the time to design and plan this process before we were moving our workloads to GCP. Here's how we do it. First, we don't use any of the basic roles, which are owner, editor, and viewer. These roles are too powerful. They grant access to any service in GCP, and they will not meet our requirements. We also do not rely on the predefined roles. Even though they are limited in what they can do, they still have more permissions than what's actually necessary. Instead, we create custom roles. With custom roles, we can define a small, granular set of permissions. Since we aren't using the basic roles or any of the custom roles or the predefined roles, we needed a way to allow access to specific GCP services. To do this, we create a custom developer role. This role is curated by us and includes permissions to all the common GCP services we use at Box. We grant this role to users and service accounts in our development environment. It gives developers the freedom to create resources and develop their application, but this role itself does not meet our least permissions requirement. So how do we go from this developer role to a role that will meet our requirements? We do this by querying the IAM Insights and Recommendations API that GCP provides. The IAM Recommender tool gives us an exact list of permissions that have been used by a specific identity. We analyze those permissions, and then we create a unique custom role based only on the permissions that were used. We then replace the developer role with this unique custom role that was tailored specifically for that identity. We don't want to have to go through this process for repeatable patterns. For those scenarios, we've created custom roles for services that are commonly used. For example, we have a custom role for Compute Engine that only includes basic permissions like the ability to log to cloud logging. If a team needs a standard VM, they can request this role, and they will already meet our requirements. This process has allowed us to reduce permissions on average by about 99% when compared to assigning a default role like editor. Now, this was a crawl, walk, run process. We started out with a completely manual task where we just copied output out of the console. We then experimented with using cloud functions to retrieve the output, and ultimately, we landed on a fully automated process that ties into our cloud onboarding procedures. Another part of our security strategy is to make the console read-only in production environments. In our dev environments, users can log into the console, they can manipulate resources. In production, the console is read-only. Users can log in, they can view their resources, but that's it. The way we accomplish locking down the console is by creating a read-only version of our developer role and assigning that to users in the production environments. There are times when elevated permissions might be needed, like during an issue. In these cases, we have a break glass process where we can assign elevated roles. We do this with conditional IAM policies with a time frame being the condition. This will allow the issue to be addressed, and the permissions will automatically be removed when no longer needed. Now that I've established how we use IAM policies to meet our requirement of least privilege, I'll tell you about our next guardrail, IAC policies. Since we require all changes to be code, we can add a governance layer that checks and validates all changes before they're applied. Org policies are at the end of the process and stop a resource from being created. Our IAC governance is at the beginning of the process and performs checks before resource creation ever starts. This is part of our defense in depth strategy. As I mentioned before, we want to shift feedback to earlier in the process and inform developers early if there is an issue. So to help provide that feedback, we recreate org policy constraints in this governance layer. If code that will violate an org policy is submitted, it will be caught before being applied. And because we have the ability to write custom policies, we're not limited to just the policies that GCP provides. Any attribute that our IAC pipeline outputs is something that we can perform a check on and validate that it meets our requirements. If it does not, we'll notify the developer and block the creation of these resources. I previously mentioned that we don't use basic roles. Currently, there's no org policy that we could configure to stop the assignment of these roles. So to compensate, we have an IAC policy that checks all IAM bindings to see if a basic role is being used. If it sees an assignment, it will block the change and inform the user that they cannot use this role. This IAC governance layer allows us to shift left by blocking misconfigurations before they ever happen and ensuring our resources are created securely from the start. Here's an example of all three of the previous guardrails working together. We wanted to give the ability for users to deploy load balancers, but we don't want them to expose those load balancers to the internet. The first problem we faced was the IAM role for load balancer creation is agnostic, meaning the same role lets you create internal and external load balancers. So we gave users that role, but we also configured the load balancer org policy to only allow internal load balancers to be created. That worked great. Anytime a user tries to deploy an external load balancer, the org policy stops it. The next problem was that the org policy stopped the deployment after the code tries to execute, and that could cause an issue with deployments. That failure was in the middle of the deployment process and left resources in a bad state, such as partially configured. And as you would expect, that was a bad experience for developers. We needed a way to validate that the org policy constraint was met before resource creation started. So we created an IAC policy to check to see if external load balancers were being provisioned. If it was, the user would get feedback during the process that they submitted the wrong load balancer and that they would not be able to move forward with this configuration. By adding a check to the beginning of the process, we were able to provide feedback early and guide the developers to a secure deployment. This example showcases our defense in-depth approach to the use of 3 distinct security guardrail controls. Looking forward, we're excited to leverage new security tooling from GCP to strengthen our security posture. A couple of the tools we're excited for are custom org policies, which will allow us to convert our IAC policies to org policies and strengthen our defense in-depth approach, and policy lifecycle management tooling to help ensure we have a safe rollout of new policies. Thank you so much for the opportunity to be here, and now here's Babak from Snap.
Thank you, Matt, for the intro and for sharing with us Box's approach to establishing secure access guardrails. All right. Good afternoon, everyone. My name is Babak Bahamin, and I am the manager of Snap's production security team. We're a group of engineers on a mission to safeguard Snap's production infrastructure and provide its developers with a secure environment to deploy and host services. Snap's adoption of Google Cloud goes back to our company's early beginnings. The backend services for our popular app, Snapchat, launched in App Engine over 11 years ago. During my 7 years at the company, I've had the opportunity to witness the evolution of our production infrastructure from a monolithic App Engine hosted service to an expansive environment powered by a diverse set of compute, network, and data resources. Today, I'll be sharing with you how Snap approached this transition, the tools that our team developed to support the company through this journey, the scale at which we operate, and some of the ways that we leverage in-house development and Google Cloud-provided solutions to harden our infrastructure and establish reliable access guardrails. At Snap, we strive to build products that are smart, kind, and creative, and we wanted an access management solution that was consistent with these core company values. For our solution to be kind, it needed to promote developer agility and give our engineers the flexibility they needed to iterate and innovate rapidly. Our desired solution would therefore need to delegate routine access decisions to the service teams, and as much as possible, remove our team from the developer request path. For a solution to be smart, it would need to continuously drive the company towards the security principle of least privilege, where all approved permissions match a recorded and valid business need. It would need to also provide us with real-time visibility into employee and service account permissions, ensure that all policy non-compliant permissions were prevented, and ensure that all policy exceptions would be ultimately funneled to our team for proper review and validation. Finally, we needed a creative approach to weave this nascent access management framework across a production infrastructure that was already serving hundreds of millions of Snapchatters every day. Said a little bit differently, we wanted a solution that would allow our developer community to retain a relative level of autonomy, but allow us to enforce a number of security guardrails as they explored new cloud services and paradigms. For this, we built an internal authorization management solution that orchestrates permissions across our entire production infrastructure. This solution includes a web portal that developers can navigate to and where they can request a number of predefined and custom roles in our GCP environment. In the example depicted here, a Snap developer is requesting object viewer permissions on a GCP project. When requesting permissions, employees can elect for time-bound or indefinite access based on their needs and use case. Once the request is submitted, it is automatically forwarded to resource owners or resource administrators for approval. At Snap, we have defined resource administrators for each GCP resource in our environment. These admins, typically the service and project owners themselves, are responsible for validating each request based on the employee's job role, the requested permissions, the requested term, and the documented business justification. Once the request is approved, our solution automatically applies the appropriate GCP IAM policies in our environment. For short-term grants, the solution also automatically revokes the policy once the approved term has expired. Finally, this solution maintains authoritative controls over all of our GCP IAM policies, and any policy configured outside of the solution is automatically revoked. From an ergonomics perspective, the solution has scaled well and allowed us to distribute validated authorization controls across a large GCP footprint. More importantly, it gave the company the necessary flexibility to rapidly iterate and over time transition out of a single Google App Engine project and into the service-oriented and mesh architecture that we operate in today. At present day, our solution handles hundreds of thousands of access requests every year and allows the company to seamlessly manage permissions for tens of thousands of identities across thousands of GCP projects, GKE clusters, and hundreds of thousands of storage resources. Next, I'll cover how our team delivers security guardrails across this expansive environment. With such powerful permissions extended to our resource administrators, we needed reliable guardrails. and mechanisms to prevent certain actions that may contravene our security and privacy policies. Here, we enforced a set of Google Cloud organization policies, like domain-restricted sharing, which establish limits on who can access our resources. We also apply additional org policy constraints that prevent the adoption of unapproved resources and services in our cloud environment. Additional Google Cloud controls, such as VPC service controls, are used to cordon off sensitive resources and prevent the data that they store from being moved to lower trust environments. Lastly, we have built custom orchestration services that block most high-risk cloud mutations. For example, these will repeal any firewall rule that may inadvertently expose our internal services to the internet. Our second set of guardrails allow us to regularly prune over-provisioned roles and stale policies. Stale permissions naturally occur over time. For example, an engineer may have acquired a set of permissions while assigned to a specific initiative, but has since been reassigned to a different product. Leveraging GCP's IAM recommender tool, we are able to constantly surface over-provisioned roles and permissions that are no longer in active use. Based on access activity over a configurable time window, the IAM recommender provides either a replace or remove role recommendation for all principals that are not taking full advantage of their existing GCP role grants. In the example here, the recommender service is letting us know that our service account is no longer using their storage object viewer role on the project, and that this policy can safely be revoked. At Snap, we've built an internal role removal service that queries the recommender APIs and automatically removes unnecessary permissions to continuously drive us towards the principle of least privilege. Staying true to our mission of safeguarding Snap's production infrastructure, we are continuously evolving and looking for new opportunities to establish reliable access and policy guardrails. From GCP product perspective, here's what we're excited about next. We're excited to see custom organization policies go GA soon, as we plan to adopt this product to help us enforce, amongst other things, GKE constraints associated with CIS benchmarks. We're also excited about the future of recommender tools on GCP. Since we make heavy use of the IAM recommender today, we're excited to see support for additional products like GCS buckets and BigQuery datasets. In addition to IAM recommender, we're also excited about similar recommender capabilities for other policy types, such as organization policies, IAM deny, and others. Thank you for your time and the privilege to speak with you here at Next 2023. Akshay, back to you.
Thank you, Matt and Babak, for sharing your approach to securing production infrastructure on Google Cloud. You've now had a chance to hear both from Box and from Snap on their approach to implementing security guardrails on GCP. You might have noticed that while their intent and their security goals are strongly aligned, their approach, the individual approach differs slightly. The phase of where you are in your cloud journey will impact the approach that you adopt for implementing security guardrails. And GCP's security guardrails are flexible enough to meet you where you are in that journey. In the last few minutes, we wanted to share more details about the future of security guardrails in Google Cloud. As part of our upcoming roadmap, we are going to be focusing on 3 main initiatives. First, we will be focused on delivering new types of security guardrails that are aimed at giving administrators even more control to help them better protect their principals, their resources, and their data. For example, we are working towards general availability of custom org policy with GKE, GCE, and GCS, and we will follow soon after with other key GCP products such as GCS. We are also working on a new control that will help administrators apply guardrails on all the principals that they manage. This security control will be able to enforce that any principal, irrespective of what permissions and access they have from IAM policies, will only have access to resources within a specified authorized boundary as defined by the administrator. Second, we will continue investing in extending the functionality of existing security controls. We will provide more flexible knobs for these controls, less restrictive limitations, and more uniform support across the entire Google Cloud ecosystem of products. And lastly, we will continue expanding our portfolio of lifecycle policy management tools. We will add uniform support for the tools that we talked about, like dry run, recommender, analyzer, across the entire security guardrails toolset. We will also extend these tools to make it easier and safer for you to deploy posture and policy changes in your environments. To give you a flavor of what is to come, here is a brief demo of custom org policy that illustrates the power of custom org policy and policy lifecycle tooling. Consider back to the use case where we wanted to deploy GKE clusters only with hardened and trusted images. To do this, I'm going to go ahead and create a custom org policy here, so something called GKE binary enable GKE binary authorization, and the goal here would be to have it act on the cluster resource type, and only for the create and update operations. Looking through GKE documentation, I've identified the knob that I want to use here to enable this guardrail, specifically binary authorization, like I mentioned. And I'm going to add that in here using CEL, common expression language, simple condition where binary authorization enabled equal to true, then and only then allow the constraint to be created. Okay, now that the constraint is created, we want to make sure that you can safely roll this out in your environments. One of the first things that is available to you as part of this is something that we call Policy Simulator, which gives you the ability to evaluate impact of these org policy changes or policy changes on your existing resources. The first step here is to define the scope of this policy change. In this example here, I want to make this policy change apply on my entire organization. Once I've defined the scope, I can now go ahead and initiate the simulator, which will check all of my resources against this new constraint that I have authored and generate a report that looks something like this. Here you can see the exact constraint that you just authored with the condition that you just designed for binary authorization checks. You can see all of the resources that would be in violation of this constraint with the full path, making it easier for you to understand what the net impact would be of this change on your organization as well as on your resources. You can also set this policy in dry run mode. Essentially, just like you would modify an existing policy or apply a new policy, you set the rules, you set the conditions, and instead of setting the policy as a live policy, you set it into a dry run mode. As you can see here, now the dry run policy is in an enforced state. Now let's say I go ahead and create a cluster with binary authorization disabled. Now this action will actually be permitted. However, we will generate a log entry for you with specific dry run metadata tagging that will allow you to compare the dry run result with the live result and actually flag the resource or the cluster that was created that is offending this specific new constraint that you're designing. Now that you're confident with the constraint that you have designed and you want to enforce it, this behaves exactly like your any other policies that you have interacted with before. I'm adding a rule, I'm setting this policy to enforced in my organization layer. As you can see here, this is an enforced state in your organization. Now let's say I try and create a new cluster with binary authorization disabled. And as expected, like with any other org policy, this is a preventive guardrail. This action will not be permitted. It will generate an error that says your resource action violates this new org policy that you've created, and you can no longer proceed. And this is exactly as we intend. With that, we have reached the end of this session. I wanted to extend a massive thank you to Matt and Babak and their teams for the continued great partnership with GCP for defining the future of security guardrails.